With the rocketing success of the Indian space program, is advanced among the world's top 4 space entities, which is driven by Indian Space Research Organisation (ISRO), the question is often being raised in comparison to military aerospace projects. Straight away, the questions hint at the development of fighter jets and, to be specific, the jet engine. While the LCA Tejas did succeed with 4+ generation capabilities, it failed to develop a viable and functional jet engine, beginning with the Kaveri engine. In fact, it is the jet engine that is still defined as the most complex technological feat in the era of artificial intelligence and machine learning. That is now set to change as the government strives to fill the technological void. The radical approach and importance that the government adopted led to 2 leading global engine makers joining hands with India. Before we continue, please make sure to like and subscribe and share the video. So let's continue. The recent talks with world-leading original engine manufacturer (OEM) Safran is a defining moment which actually lays the foundation of a new jet engine with best-of-class thrust ratio to power next-generation 5+ fighter jets. However, it is important to understand what is actually needed to develop a jet engine which could power India's highly ambitious programs like Advanced Medium Combat Aircraft (AMCA), Multi-Role Fighter Aircraft (MRFA), and possibly Tejas Mk2. The technological gaps are well understood now, as India learnt during the development stage of the Kaveri engine, which was sanctioned in 1989 for LCA Tejas. Propulsion technologies. The jet engine is fundamentally all about the 3 highly complex core elements: advanced materials and process technology, combustion technology, and computational fluid dynamics (CFD) in engine design procedures. Worldwide, all gas turbine engines have now improved turbine inlet temperature and compressor pressure ratio. The core functional aspect of the turbine has been transformed with a greater bypass ratio and nacelle performance, which also boosts emissions. The Kaveri turbofan engine faced thrust deficit performance at high altitudes, excessive weight, and a mysterious noise. The noise that emanates from the excessive heat in the core could not be rectified, but that corresponded to the material within. The material in question is the superalloys, which can withstand combustion heat beyond 1800 degrees Celsius. To generate 110 kilonewtons wet and 75 kilonewtons dry thrust aimed at new engines for Indian fighter jets, the higher heat resistance materials were needed. And that is about finding high temperature materials mix and technology to process it for jet engine. Mostly, silicon carbide (SiC) and ceramic matrix composite systems are the proven ones for jet engines, which India lacked. Besides, ceramic matrix composite materials are a choice for aerospace structural parts, which are largely utilized by the world's leading global engine manufacturers, Safran and GE among others. Despite the challenges, ISRO has successfully used such complex materials, especially carbon-carbon composites, for aerospace structures in the parts of gas turbine engines such as flaps, vanes, seals and liners. That remains for India's ingenious plan for jet engine. That is where the recent development and foreign collaborations matter, where India needs to address the ceramic matrix composites (CMCs) for engine, especially the core. Both global leaders of the jet engine, Safran Aircraft Engines and GE, can resolve the materials issues. In fact, jointly, Safran and GE have established an entity which is known as CFM Materials for their existing and futuristic jet engine. Safran HAL co-development. Once we cross the materials issue, the next stage is about developing capabilities for the supply chain of components and ancillaries in India for the next generation 110 kilonewtons engine for AMCA and MRFA. Safran is already heavily investing in 6th-generation fighter aircraft with afterburner thrust of 125 kilonewtons. That, if it is well negotiated, will design and develop a 110 kilonewtons engine with India without any hiccups and clauses, which is prevalent in the inner world of elusive jet technology. Here, the collaboration will enable critical cast components of titanium and superalloys. India can not only leverage Safran's M88 engines which power Rafale fighter jets, but the new engine for military aircraft engine and other critical applications. Collaboration is a much better option for India as it tests our real ambitions and efforts for such high tech. DRDO's gas turbine research engine, GTRE, has achieved some good fundamental success in single crystal blades where the French giant Safran will play an immense role, which includes the core material, computational fluid dynamics and heat management, etc. In fact, Safran has proposed a better engine core than M88 which powers Rafale. Besides, Safran helicopter engines and HAL are already in the process of setting up their new joint venture company in Bengaluru, which will be dedicated to the design, development, production and support of helicopter engines for the 13-ton Indian multi-role helicopters IMRH and its naval version, the deck-based multi-role helicopter DBMRH. In fact, elaborating on the proposed collaboration, Cedric Gubit, CEO of Safran Helicopter Engines, explained, "We at Safran Helicopter Engines are truly elated to partner with HAL and India to craft this new turboshaft engine joint venture set to address the Indian market and also future export opportunities." Safran's Ardiden 1H1 engine with Hindustan Aeronautics HAL, is later called Shakti, is one of the most successful high-tech military projects which powers India's all-indigenous helicopters, including the Advanced Light Helicopter ALH Dhruv, ALH Rudra and Light Combat Helicopter LCH Prachand. Here, the scope of tech collaboration has touched the engine manufacturing process in its entirety, including the two-stage centrifugal compressor, single-stage gas generator turbine, reverse flow combustion chamber, two-stage free power turbine, gearbox unit and dual-channel FADEC full-authority digital engine control. HAL will further leverage the compact modular design of Shakti 1H1 for IMRH and high-altitude sustained capabilities in extreme conditions. Apart from fighter jet engine, the civil space is also witnessing unprecedented demand for aero engine. For example, the LEAP and its predecessor, CFM56, which power over 330 Airbus A320, A320neo and Boeing 737-737 MAX aeroplanes are operational in the Indian subcontinent. With 1,500 LEAP engines currently on order, Safran is also establishing a maintenance, repairs and overhaul MRO facility. Later, Safran is also planned to build parts. According to a recent study, the aero engine market is expected to grow from $54.7 billion in 2022 to $112.6 billion in 2029 at a CAGR of approximately 11%. India is expected to order 500 military aircraft over the years. Broadly, taking account of services requirement, there will be a demand for 2,700 turbine engines for fighter aircraft, including those for replacement and trainers, and over 5,000 helicopter engines of various classes.